This is Earth Science Lecture 4 on minerals. We'll first start this lecture looking at what an element, atom, and bonds are, and then we'll get into some of the key properties that are used to identify minerals. These are the properties you're also going to be using when you do your minerals lab exercise. And then we'll see what the difference is between a mineral and a rock. So let's first start with elements and atoms. What are these? Well, the smallest, most fundamental substance into which matter can be separated using chemical means is what an element is referred to as. Elements have different characteristics, and they're made up essentially of atoms. The smallest part of an element is basically what an atom is. An atom is the smallest individual particle that retains distinct chemical properties of an element, and it's the periodic table that lists the known elements that we have in nature. There's about 112 known elements and about 20 that have been man-made. Atoms can, though, be further broken down into subatomic particles, and that's actually what's shown here in this figure. This is a cartoon showing the internal structure of an atom. An atom has a central nucleus, and within the nucleus you have subatomic particles, sub meaning smaller than the atom, subatomic particles, proton and neutrons and electrons. Protons and neutrons are both found in the nucleus. Protons are positively charged and neutrons have no charge. What we have orbiting the nucleus are electrons, and electrons are negatively charged. All atoms, if they are uncharged, meaning if they're not ionic, basically have the same number of positively charged protons as they do negatively charged electrons. And so some other things that you can learn about atoms are the atomic number and the atomic mass. And both of these are given by the periodic table. The atomic number is essentially the same as the total number of protons in the nucleus. And so if we take a look at the periodic table, let's just look at carbon, because I happen to be quite partial to that element. Carbon, you notice each of these elements listed has a number written in the upper left-hand corner. That's the atomic number, and it basically tells you the number of protons in the atom's nucleus. And so carbon has 6 protons in its nucleus. If we change the number of protons in a carbon atom nucleus to, let's say, 7, we no longer have carbon, because if it has 7 protons in its nucleus, then we have instead nitrogen. So let me go back to the PowerPoint and we'll look at the second term I wanted to define on this slide, which is the atomic mass. The atomic mass is measured in what are called AMU, or atomic mass units. It's equal to the total number of protons plus the total number of neutrons in the nucleus. You might wonder where that third subatomic particle is listed, the electron. Why isn't the electron part of the atomic mass? Well, the reason why it's not included is the electron is about 2,000 times smaller than protons and neutrons. So it's the same thing as if I were taking your weight, you were standing on a scale, and I put 4 coins in your pocket, and I took your weight again. It really would not affect your weight by very much. So we just choose to exclude the electrons from the measurement. So if I go back to the periodic table, carbon, you will see, has an atomic mass of 12.011. What we'll see later in the classes, if you're wondering why this is a decimal, if it's protons and neutrons, which are integers, they're not decimal numbers. If we're adding 2 integers together, how do we get a decimal? Well, all carbon in nature does not have the same mass. You could have carbon with a mass of 12, meaning it has 6 protons and 6 neutrons. You could have carbon with a mass of 13, which would be 6 protons and 7 neutrons. So the number of neutrons can actually vary, but if the number of protons varies, you get a different element altogether. We'll see this later in the class, but I just wanted to introduce it here because it's mentioned in your textbook. So going back to the PowerPoint, let's look at bonding. Now bonding is pretty amazing because this is actually one of the strongest forces in nature. Of all the forces we could think of in the physical world, the force that holds atoms together in a chemical compound can be very, very strong. And actually, the second type of bond in this list, the covalent bond, is the strongest bond in nature. We're going to see that this is relevant because when we talk about mineral hardness, the hardness of a mineral, like you might know diamonds are the hardest substance on Earth, the hardness is directly related to the type of bond within the mineral. By the way, I'm not interested in you memorizing the different types of bonds. I just wanted to introduce it here because I think it's relevant. Ionic bonds. Ionic bonds are where an atom transfers an electron to another and it creates a bond. These bonds have a moderate strength. They're pretty strong. As I mentioned before, the covalent bond is the strongest bond in nature. This is actually where electrons are shared. So instead of being transferred from one to the other, a single electron is shared by different atoms. The van der Waals bonds, which are the fourth one listed here, they're very weak, and they actually really just involve not even the electron and the proton or different charges. It's really just because of the arrangement of how the atoms are within the structure that gives it more of a positive nature in one region and more of a negative nature in another, but they're very, very weak forces. And we'll see when we look at graphite in class how it's one of the reasons why this mineral can break apart very, very easily. The last bond worthy of mention is the metallic bond. This is where electrons are shared among several atoms. And typically these are very good conductors of electricity, and they give metals their really malleable characteristics so they can bend really easily. So we're going to talk about mineral properties in a moment, but I'd first like to talk about what the definition of a mineral is. So these are the components that a mineral needs to have. It must be naturally occurring, inorganic, solid, orderly crystalline structure, and have a definite chemical composition. So what do these mean? Naturally occurring means it's formed by natural geological processes. It's not synthetic or man-made. Inorganic, not from living organisms. This is a tricky one because inorganic is sometimes used to imply that a substance does not contain carbon, like if you've heard of inorganic chemistry and organic chemistry. But in our definition for this class, it basically means it's not from a living organism. Some of you might know the rock coal. Coal is actually the remains of plants and animals that were living on Earth millions of years ago. Coal would be something that's not a mineral because it's formed from living things. Now, what do we mean by solid? Well, if you're at Earth's surface, the temperatures and pressures that you're experiencing at that location, it's in the solid phase. So therefore, it's not in the liquid and it's not in the gas phase. Now keep in mind, anything, if heated to high enough temperatures, will melt and will vaporize. Rock can actually vaporize if you heat it high enough temperatures. And so what this implies is that when you are at Earth's surface, it's the right temperatures and pressures to make it solid. The next one is that it has an orderly crystalline structure. So the atoms are arranged in a very orderly, repetitive manner. If you take a little piece of it in the corner, you have exactly the same pattern as in another little piece of the mineral. The last one, it's represented by a chemical formula such as SiO2. That's actually the chemical formula for quartz. The latter two of these parts of these definitions are things that you probably won't know when you're examining something, but do know that minerals all have very distinct elements within them. It's not just a random assemblage. Now, let's look at some of the mineral properties. There are some that are very common, which you're going to be measuring, especially when you do your lab, but we'll also look at these properties in class. Luster, color and streak, hardness, cleavage and fracture, and crystal form. These are really common ones that most minerals will exhibit. And then there's a group which I like to call other, because usually it's just one mineral out of all the minerals that you have that will exhibit this particular property. So let's look at the definition of these mineral properties. First, let's start with luster. Luster means how a mineral reflects light. And so when you pick up your sample, you turn it around in the light and you see what it appears like. You can basically define a luster as being either metallic or non-metallic, and that's the first grouping that you put the mineral sample into. Does it look like a metal? Does it look silver or gold? Or not metallic? Actually, if the mineral is not metallic, it's usually very useful to describe it in another way if possible. It could appear glassy or vitreous. It could look like a pearl or be called pearly. It could be kind of waxy, resinous, or earthy and dull. So it basically has no shine at all. So in lab, you're going to want to try to use these terms to describe the sample that you're looking at. The next property is called hardness. Hardness is a resistance to an abrasion, and it's basically related to the type of chemical bond that's within the mineral holding the individual atoms together within that crystal structure. A harder mineral will scratch a softer mineral. The hardest mineral in nature is a diamond, and if you have a diamond, you could scratch any other mineral with it. We actually use a scale called the Mohs hardness scale to measure a mineral's hardness. And rather than walking around with all sorts of different minerals and testing which one is softer and which one is harder than the other one, what we use are common objects, which are listed here. We use a glass plate, and in lab you'll have these to use, and we use our fingernail. The glass plate has a hardness on the Mohs hardness scale of 5.5. The fingernail has a hardness of 2.5. This hardness scale is a relative scale. The numbers really are just which one is greater than the other. But if we actually looked at which one is super hard, diamond on the absolute hardness value is significantly harder than corundum, which is a number 9 on the hardness scale. Corundum is like ruby or emerald. So there's a very significant jump when we go up to diamonds. It's significantly harder, but again, we just use this simple hardness scale. And so with the hardness scale, we use these common objects to measure a mineral's hardness. If you have a glass plate and you could scratch the glass with the mineral, it means that the mineral is harder than the glass. And so if the glass is 5.5, then the mineral has a hardness of 5.5 or more. Likewise, if you could scratch the mineral with your fingernail has a hardness of 2.5. You've scratched the mineral with your fingernail, so that means your fingernail is harder than the mineral. That means the mineral's hardness is smaller than 2.5, so 2.5 or less. Of course, you could also have the example of something in between the two, and if it were in between the two, what that would mean is that you cannot scratch the glass, it's softer than the glass, but you also can't scratch it with your fingernail. It's harder than your fingernail, and so in that case it would be 5.5 to 2.5. You'll get a lot of practice with that in the lab, and you'll be the expert, I assure you. Now, color might seem to be the most intuitive property, but it's actually considered to be the least useful. You're going to see when you go to do the lab that many, many minerals have exactly the same color. There's lots of white and clear minerals. Likewise, one mineral can have many different colors. Like, for example, in this picture, you have all the different colors of the mineral quartz. Different colors result from small impurities in the mineral, so it's not always very useful. Another thing you'll measure in the lab is streak, and this is basically the color of the mineral when it scratches off on what's called a streak plate. A streak plate is a plate of unglazed porcelain, And the color that you see when it rubs along the streak plate is essentially the true color of the mineral. You might know that some minerals may rust when they're exposed to air in the atmosphere, and they might turn into a different color. So the streak often will tell you what the true color of that mineral is. But interestingly, not all minerals have a streak. The streak plate itself has a hardness of 6.5. So if you have a mineral that is harder or has a hardness number that's greater than 6.5, it will not scratch off. And so you basically put not applicable for its streak. It doesn't have one, or you could put a big X in the box when you do that in the lab. Cleavage and fracture. Now, certain minerals, when you break them, they demonstrate what's called cleavage. And cleavage means that when you break the mineral, it breaks along flat, even surfaces, which are called cleavage planes. These are actually zones of weakness, which are created by weak bonds in the crystal structure. We define these by the number of directions of cleavage and the angles between the planes, which we'll look at in a moment. Now, if a mineral breaks along a flat surface, we say it has cleavage. It could break along one flat surface, two flat surfaces, three flat surfaces, four flat surfaces. If it breaks on any number of flat surfaces, it has cleavage. If it doesn't break along a flat surface, if it breaks with an irregular pattern, then we say the mineral has fracture. So cleavage and fracture are an either or. Minerals will not have both. Now, to determine the number of cleavage directions, imagine I put in front of you a cube. The first thing you do is add up the number of planar sides, so the sides that are flat surfaces. So if you have a cube, you might think of a dice. It has 6 sides. You're going to subtract off the sides which are parallel. And so on a dice, the top and the bottom are parallel. One side and the other side are parallel, and in the other direction, the sides are parallel. So there's 3 sides that are parallel. So when you do the subtraction, we initially have 6 planar sides. We subtract 3 sides which are parallel. The answer tells us the directions of cleavage. So we would say a cube has 3 directions of cleavage. If you have mica, which is shown in this top picture, mica is like a deck of cards. In a deck of cards, you would have many, many flat surfaces, but all of them are parallel to each other. So if you were to look at the top card and the bottom card, we have 2 parallel surfaces, but one is, we have 2 flat surfaces, but one is parallel to the other, so we subtract 1 from it, and we're left over with 1. And so the micas are called those that have one direction of cleavage. In this bottom picture, this purple mineral is like a pyramid on one side, and then there's a pyramid on the back side that you can't see. That's an example of a mineral with 4 directions of cleavage. This is the one from the previous page with 3 directions. And this rhombohedron also has 3 directions of cleavage. This is something that you'll be doing in the lab, and believe me, when you have a sample in front of you, it's a lot easier to see. So your lab instructors will help you with this, I'm sure. So now with the 2 that have the 3 directions of cleavage, we can also describe the angles between the cleavage planes. And don't worry, you don't have to take out your protractor. You're basically just going to look at the cleavage planes to see if they're at right angles or at 90 degrees or not at right angles. And that's the way that you'll be defining these in the lab. So notice the mineral on the right here, the angle between these cleavage planes is not 90 degrees, where here it is 90 degrees. I see a nice 90-degree angle there. Some other characteristics. If a mineral demonstrates fracture, sometimes it has what's called a conchoidal fracture pattern. This often is what it looks like when you break glass. And in these 2 samples, we have quartz, which is actually what glass is made up of. You get this very cool kind of shell-like shape within the structure. So it's named for that shell-like shape that's here. Let me see if I could just sketch that on here for you. So if you look at this picture, you could kind of see these shells. Let me change my pen color. Over here, I could see some kind of curved lines So sort of named for like the shell-like appearance of the fracture pattern that occurs. Now, all minerals will grow a crystal. It's an expression of that orderly, repeated pattern of how all the atoms are within the mineral structure. Although you often won't see this because a mineral needs a lot of space and time to grow. But if it does have space and time to grow, you will see the true crystal structure forming. If you've ever seen a geode that somebody's cracked open, there's some space inside of that so the crystals can grow. So they're very rare to find, but that's also a part of the structure that you could see. So sometimes you'll read a description of what the crystal shape is like, and that helps you to identify the mineral. But looking at this picture, you might notice that crystal faces also have flat surfaces. So how do I know if this flat surface I see on this quartz crystal is cleavage or if it's fracture? Well, what you'll do, since the properties look similar, what you need to think about is if you were to break the mineral. If you break the mineral, it's going to break along a cleavage plane if the mineral demonstrates that. And going back to this quartz crystal, quartz actually only shows fracture. It doesn't show cleavage. And so if you were to take this beautiful crystal and break it, which you will not be breaking things in the lab, but we'll talk to you about how you could see what they look like when they're broken because we have some samples in the lab room for you, you could see. So the flat surface we see here is crystal form because if I were to break it, it would not break along that flat surface. It basically grew a crystal, but it will fracture. It is actually possible for a mineral to have both crystal form and cleavage. A crystal can grow and it could also break along a cleavage plane that's similar to its crystal shape. Calcite actually has that property. Magnetism. That's a pretty simple property. That's if the mineral attracts a magnet. So it's tested using a magnet. But you'll actually find, to many students' surprise, that not all metals are magnetic. There's the fun test in the lab called the fizz test. You use a very, very dilute acid called hydrochloric acid. And if the sample has calcite in it, calcite actually fizzes when the acid is applied. What's happening is the acid is reacting with the crystal, and what's being released is carbon dioxide, so it fizzes and bubbles up just like a carbonated beverage. Since you're testing to see if you have calcite when you do the fizz test, because calcite is the mineral that fizzes, calcite will only be white or clear. So you only have to test minerals that are white or clear to see if they're calcite. You don't have to test the metals and the dark samples. There's taste, and I should not have to tell you this, but the samples should never be tasted from the lab. But if you were to taste it, if it was a very clean sample that had never been touched by hundreds of students and hadn't have acid put on it by hundreds of students, and you could put it in your mouth, if it has a taste, then we can record that. And the mineral halite actually has a salty taste. There's a property called biorefringence. This is really cool. When light goes through the mineral, it's split, so you see a double image. And so calcite would actually show this. And so if you look at this image up here, there's a sequence of dots on the piece of paper, but when you look through the mineral, you see 2 rows of the dots. That's the biorefringence, or double refraction, that the mineral is doing. The next property is fluorescence. This is cool. If you use an ultraviolet light, sometimes known as a black light, the mineral might glow in particular colors. So sometimes that's how particular minerals are identified. Actually, diamonds have a specific fluorescent color that they produce. There's something called striations. Striations are lines or stripes that occur within the mineral. And there's also how the mineral behaves when it's bent or when you try to deform it. It could be brittle and just shatter. It could be malleable and bend like a metal. Think about of aluminum foil or something like that. It could be elastic, so you could stretch it and then it snaps back to its original shape. It could be flexible, so you could twist it and bend it, but not necessarily snap back to its original shape. So we will be examining all of these properties more in our lecture. So we will actually look at some samples and examine their various properties. So but you should definitely look over these terms as we've gone through them. The last thing that we'll examine in this lecture is just what is it that makes a rock, and how is that different from a mineral? Well, the difference between the two, if like you look at this picture, I have the rock, granite. Granite has a little bit of this gray mineral in it, a little bit of this black mineral in it, a little bit of this pink mineral in it. So rocks are typically composed of one or more minerals. So minerals are the individual components of rocks. So for example, the rock granite is composed mainly of the minerals quartz, hornblende, and feldspar. So I'm ending the lecture here.